All right, this is our video presentation for Opti 380A, communication high speed and internet.
All right, for our project, we wanted to develop a method to test a plastic fiber optic used for short-range communicating and sensing. So for our experiment, we wanted to understand the performance capabilities and performance limits of our plastic tube. Our objectives were to measure the time domain and power domain, and then also measure the key characteristics, including the attenuation, SNR, and the bandwidth frequency response. And so the significance of this experiment is to demonstrate the effects of fiber optics length, the angle attenuation, and then the effects on signal power and SNR loss, and the limitations put in place on long-range communications and its measurement of uncertainty.
For a little background, fiber optics are used widely throughout communication systems as they outperform copper wires in many ways. There are significantly less losses, but they still exist. Next slide. Fiber optics work through total internal reflection, which is a unique case of Snell's law. As the angle of incidence gets high enough, transmitted light will reflect perfectly back into the fiber optic cable. Next slide. There are a few sources of losses still. Absorption occurs as light dissipates in the material. With sharp bends in the fiber optics, rays can still escape. And there are Fresnel reflections, which are losses at the interface between, or when light enters and exits the cable. These losses can lead to higher attenuation coefficients and lower signal to noise ratio.
As for our experimental design, we had to break it up into two phases. The first one being temporal response and the SNR, which we use the oscilloscope for. First, we align the LD and place an aperture, then putting the PMMA fiber on a translation stage and placing the PIN photodiode in direct contact with the fiber. We wired that to channel 2 of the oscilloscope and then used a function generator to create a square wave with a modulating intensity from channel 1. We made measurements such as the peak-to-peak and VRMS at multiple frequency while still qualitatively analyzing the bending aspect. Phase 2 was for attenuation. We used a straight fiber configuration and measured the input optical power and kept that constant. We then inserted the fiber and measured the output power in direct contact. And keeping the input power constant, we measured the output power for different lengths and then adjusted the radius and measured the output power of that as well.
For phase 1 of the lab, we were able to calculate the temporal response in SNR. Qualitatively, as the modulation frequency increased from 1 kilohertz to 1 megahertz, the output voltage of our system dropped from 1.5 volts to 0.21 volts, while the SNR decreased from 34 decibels to 6 decibels, demonstrating a low-pass response in our optical fiber, basically saying our optical fiber limits higher frequencies from transmitting within. With a rise time of 104 microseconds, we calculated the effective bandwidth to be approximately 3.4 kilohertz, quite low, meaning our optic has a lot of dispersionary effects at higher frequencies. On the next slide, for attenuation, the total loss in our system increased with fiber length, while the attenuation coefficient increased for shorter fiber lengths. This means that although the total loss is lower for shorter lengths, it also has a higher loss per centimeter. On the next slide, we tested the angle of fiber optic versus the power. As the angle increased, the output power decreases. Simply, this is due to the light leaking out of the fiber optic as it no longer has efficiently used TIR, leading to a higher attenuation loss per angle. On the next slide, it basically is what I just discussed now, similarly on the next slide as well.
Some of the limitations and sources of error were the manual alignment and, most importantly, the poor quality of the fiber optic we used. It wasn't long enough and it was plastic with no cladding on the outside. Another aspect was the light from the source was not collimated. A future improvement we would do is get a higher quality optical fiber and have a more precise system properly aligned.
And here's our contribution page. Take a look and thank you.